Okie doke. All right, well, let's go ahead and get started here. Okay, we need to finish up. We need to finish up where we're at, and hopefully we might have a couple of minutes at least to do some review, especially Chapter 5. Chapter 5 stuff is by far, I think, the harder of the stuff, just because there's more stuff to set up. I mean, more than anything else, it's just a lot of detail in Chapter 5. I don't know if I'll get to it or not. I don't know, but I would suggest that you work as many red problems as you can. Okay, go back through Chapter 5. It is on the test on Monday. It is on the test. And there's a lot to it. There's a lot to it. So let's go ahead and finish up. What chapter is this? Let's go ahead and finish up chapter 9. We're not going to do all of chapter 9. The stuff on molecular orbitals, MO theory, we're not going to do, and we're not going to do that because neither one of my colleagues, that's not one of the things that they're into. So when you get into 152 and 251 and 252, you may or may not see that there, but we're not going to do it here. Okay, so we're going to kind of skip over molecular orbital theory in case you're thinking about it. Personally, I would do it, but we just don't have time. I mean, that's really what it comes down to. Okay, so let's continue on. And so we had this sort of situation going on here. We had, let's say we had PO43 minus, otherwise known as the phosphate ion. And I believe this might actually be on the lab number 10. I think this might be one of them that's on lab number 10. And if you go through and you do the Lewis dot structure for this guy, you would get the following. Here is one possible structure that you could get. And I'm just going to draw it out. And I'm using lines because I just think they look cleaner to use lines for single bonds. And you would get this guy right here. And of course, if you really want to be complete, you would put a 3 minus on the outside. And you would say to yourself, well, that's a wonderful looking Lewis structure, because if we look and check and see and make sure if everybody is happy, like that phosphate, for instance, you would say 2, 4, 6, 8. It has 8 electrons on it. And if you were to look at, say, these oxygens, you would say that they're also very happy because they have 2, 4, 6, 8 electrons on each one. And you would say, hooray. All right. And you would be right. It is a valid Lewis structure. But there's actually, if you experimentally look at this guy, you would see that in reality, that this guy looks like this. Now remember, we have theory and then we have reality. All right, so we have to make our theory fit our reality. So if you look at this guy, this is what you'd find experimentally. Let me make sure I put on all my electrons. Okay. And you'd have 6 non-bonding on 3 of them and 4 non-bonding on the one that's double bonded. And this is the actual. This is actual. All right, so what's up with this? Okay, and by the way, how many resonance structures would you say for this? How many would you say? Just hold up your fingers. What do you think? How many resonance structures? 4, right? Because you could walk that double bond around, right? How many resonant structures would you expect here for O3? You would expect 2. Very good. See? Okay, easy peasy, huh? We should be able to look at that. But here's the actual. So what we're going to call is something called formal charges. What formal charges does is it's based on oxidation numbers. Okay, it's based on the idea that we want to minimize the charges, and we're not talking charges as in, an actual plus minus, but we're going to use this as a tool to try to decide what's the best structure, So this is for the best or most favored. Okay, now formal charges will give you an idea what's going on. It won't tell you for sure that this is the best. You still have to go do an experiment and you still have to look at things. Just like, the one on the left-hand side, we figured out doing Lewis dot structures like in Lab 10, but it turns out not to be the case. So we need something to explain that. And the way we're going to do this is we're going to do what's called valence and assigned, valence minus assigned, and we're going to do formal charge. Okay, now, and let me just drop this guy over here so it's lined up. Okay, now, the valence charge on each one of these atoms, the phosphorus and the oxygens, each one is going to be the same regardless. All right, that you just look at the periodic table to find the valence. Okay, so you go 1, 2, 3, 4, 5, 6, 7, 8. You just kind of go across and you just decide based on that. Now, before we start doing this, there are two kinds of oxygens. We have oxygen number 1 here. That's the one that's double bonded. And then we have these guys. Okay, I'm just keeping track of them. Those are single bonded oxygens. So we have two kinds of oxygens, all right? Obviously there's only one phosphorus, so we just have the one phosphorus. And let's do this over here too as well. We'll call this 2, 2, 2, and 2, because those are single bonded oxygens. And we'll say this is phosphorus, we'll say this is phosphorus over there. So we're gonna do the same for both, all right? And we're gonna compare the two. And then I'm gonna show you what I mean by one is more favored over the other. All right, so let's do. Now, when we say valence versus assigned, valence, we're just going to go ahead and do that. So I'm going to say oxygen. We're doing the left-hand one. And so what do we have for valence electrons for oxygen? We look across our periodic table and we go 1, 2, 3, 4, 5, 6. We have 6 valence electrons for all the oxygens in that first one. Now, assigned is going to go like this. I'm going to put it over here in blue. I'm going to say assigned. That is non-bonding plus 1/2 shared bonding. Okay, so how many assigned do we have here on the oxygen? We have these guys right here, and they're all the same. That's 6 right there. That's 6. But what do we have here? We have 2 electrons that are bonded, and we want half of those because we're going to say one of them goes to one and one of them goes to the other is what we're saying. So that is 6 plus 1 gives me 7, and we're going to subtract off that 7, and we're going to say the formal charge on each one of these oxygens, the formal charge is -1. I'm going to put it in blue. Now let's do the phosphorus. So we say, what's the phosphorus? Well, the valence electrons on the phosphorus, we look and we go, here's phosphorus below nitrogen, and we go 1, 2, 3, 4, 5, and we say 5 on the phosphorus. That's the valence electrons. Doesn't matter whether it's double bonded, single bonded, triple bonded, whatever, it's 5. Now, assigned. How many do we have that's assigned? And so we go, there's 2 here, but that's 1. That's 2 there, that's 1. There's 2 there, that's 1. And there's 2 over here, that makes 1. Remember, it's 1/2 of the bonded. There's no non-bonding on that phosphorus, it's all bonding. So we have 4. So we subtract off the 4 and we have +1. So the formal charge on this phosphorus is +1. Now look, if you add up all these formal charges, what do you get over here? You got 4 minuses and a +1. Well, 1 minus 4 is -3. So the charges add up. Now, word of caution, it's not an actual charge, but they do add up. All right, they do add up. All right, now let's take a look at structure number 2. And we look at structure number 2, and the sign are gonna be the same, but we're gonna call this oxygen 1, oxygen 2, and phosphorus. Okay, because they're different. Now, oxygen number 2 is the same. It's still what is that? That's 6, and let me move this 6 up because I need to move these guys up for my table purposes. So let me get this back up here so I can give myself a little bit of room here. So oxygen 2 is the same as the green oxygen 2s. Let's just do that. We got 6, and we had 7 on each one, right, on the green number 2s, and we had -1. So these are still -1 up here. So these are still -1, -1, and -1. They're still -1. Okay, because they're still single bonded oxygens. There's still 6 valence electrons, and there's still 7 assigned. All right, I just saved myself a little bit of time. All right, now oxygen number 1, which is this guy right there, now it's still 6 valence electrons no matter what. But what do we have here? We have these 4 right here, and we have 1, 2, 3, 4, but half of that is 2. So 2 and 2 make 6. And so the formal charge on that oxygen right over here is 0. On the double bonded oxygen, it's 0. All right, now the phosphorus down here, what do we have here? Well, the phosphorus is still 5. Remember, the valence electrons don't change. It's still 5. Well, what do we have for assigned? Well, we have 1 from here, 1 from here, that makes 2, 1 from here, that makes 3, and then we have 2 more up here with the reds, and that's what? That's 1, 2, 3, 4, 5, so that's 5. 5 minus 5 is what? 0. So the formal charge on that phosphorus is 0. Now, hopefully everything adds up to -3. And we add up these red -1s, and we get 1, 2, 3 -1s. That's -3, and then we got a 0, 0. So the whole thing is still -3. This is good. The whole thing is still -3. Now, what makes one better than the other? Well, what we're going to do is we want to ideal, best. We're going to say best is all zeros. Okay, but if we can't have all zeros, we want to put the minus on electronegative, and we want to put a plus on the electropositive. Okay, so out of the two, what's most electronegative? The oxygen is most electronegative. Out of oxygen and phosphorus, oxygen is further over on the right-hand side, and it's closer to the fluorine, so it's more electronegative. Okay, so oxygen is much more electronegative than phosphorus. So sure enough, we have -1 in both cases. So the -1 is on the right element. The -1, the minus charge should be on the oxygen, if you have to have one. If you have to have one. Ideally, we don't want any charge at all. So sure enough, the oxygen is -1. But what do we see here? We see that we have 4 that have -1s on them, and we have a +1 on the phosphorus. Now, if we look at the right-hand side one, now in this case, we have only 3 that have charges on them, and we have the ideal situation. What's the ideal situation? The best situation is no charge at all. And so the right-hand one puts 0 on 2 of the elements, whereas the one on the left-hand side has charges on everybody. So we have minimized the charges that end up on the elements on the right-hand side, right-hand side molecule with the double bonded. Do y'all see that? You see what I'm saying here? This is how we can tell the difference between the two. Okay, so this is the most favored of the forms. That doesn't mean the one on the left-hand side doesn't exist. It just means that the one on the right-hand side is by far more favored. By far more favored. Okay, and if we go through the same process with some other things, such as NO3 minus, for instance, we ought to, if after we're done, we ought to end up with something that looks like this. Okay, and if we do the same thing with, say, let's see, SO4, we should have PO4. Yeah, we should have the same sort of situation. Okay, we should end up with double bonds is what my point is. Okay, because if you go through and you check for formal charges, that's what's going to happen. Okay, SO4 2 minus, there it is. Okay, so you should end up with the same sort of situation. And we'll do it by formal charges. And I think I'm going to go ahead and do an extreme examples here. Let's do CO2, just to show you one more example of the difference of formal charges. And let's do like this. Let's see if I can make this happen. Something really strange here. And we'll drop that back there. We're going to keep that here like that. Yeah, let's do that. This should be the same situation. Let's say we have choice between these two guys right here. All right, one on the left-hand side is by symmetry arguments. It should be the right one. The one on the right-hand side is still a legitimate, let's see, we should be able to drop this guy in. Yeah, let's drop that guy in right there. There we go. All right. 1, 2, 3, 4, 5. 1, 2, 3, 4. Let me make sure. Yes. Okay. One on the right-hand side satisfies the Lewis requirements. Okay. It looks a little strange compared to the left, but if you look at this, what do we have sharing here? We got 2, 4, 6, 8. What do we have sharing here? We have 2, 4, 6, 8. What do we have sharing here? We have 2, 4, 6, 8. Okay, so it's happy. So let's compare these. So we have carbon, oxygen, and they're both the same. We have 4 and 6, and this is valence. This is assigned. How many we assigned on that carbon? We have 1, 2, 3, 4 assigned. That's 0. And the oxygens, we have 1, 2, 3, 4, 5, 6 assigned on each one. So 0, 0, 0 all the way across. So everybody's happy. Lewis dot wise and formal charge wise, they have zeros on all of them. Now, I already decided that from a Lewis dot and octet rule standpoint, the structure on the right-hand side is okay from a Lewis dot standpoint because everybody's happy with 8 electrons, right? But let's see what we have here. Now, carbon is still 4, and each one is still 6, okay? But let's check it out. Now, the carbon is still 1, 2, 3, 4. Remember, it's half of the bond. Each bond is 2, and it's half of the bonds, right? So we have 4 bonds. That's 4 electrons. So carbon's still happy. That's not a problem. But let's take a look at these oxygens. Let's take a look at these oxygens. And if you take a look at, we're going to call this one oxygen number, let me change the color here so it's more obvious. We're going to call this oxygen number 1, and we're going to call this oxygen number 2, okay? So oxygen number 1, what do we have? We have 1, 2, 3, 4, 5. We have 5 assigned. That's +1. Oxygen number 2, how many do we have assigned? 2, 4, 6, 7. Minus 1. And so oxygen number 1 is plus 1. Oxygen number 2 is minus 1 for formal charges. It still adds up to 0. 1 minus 1 is 0, so it's still a neutral molecule, so that's okay. But what's the rule here? We want to minimize the charges. In other words, 0, 0, 0 is absolutely minimized. This has got, first off, the charges are not minimized in the right-hand side one, but not only that, but look here. I got a plus 1 charge on an electronegative element. That's bad. This is bad. That's bad. Oxygen's not going to like it. This one's not bad, but we have charges when we could be 0. All right. So it's a decision-making process. Okay, I'm not implying that at any time is it a plus 1 or minus 1 on these molecules. It is a decision-making process as far as what is the best, most favorable structure. Okay, that's all we're trying to do here. I'm going to leave this at this for formal charges and say the following. Formal charges overemphasize oxidation numbers. That's what formal charges do. So they have their limitations. They overestimate the importance of oxidation numbers. Lewis dot structures overestimate the importance of full valence shells. So each one has its advantages and disadvantages, okay? And that's all I'm saying here. They're just tools. They're just tools between the two. All right. So that's that. Okay. Now, the last little bit that I want to go through here before we get into hybrid orbitals, which will be where we finish off on this chapter, is the idea of polar molecules, okay? And bonds. All right, now, we did bonds. We did bonds. How did we know if a bond was polar or not? We would look and see if they're left to right of each other at a first approximation. Okay, we can look at the BIs and we can look at, you know, some tables and take differences of electronegativities between the two. But if they're left to right on a periodic table, they're going to have differences in electronegativities if they're left to right on the periodic table. And so a CF bond would be polar. Okay, whereas say a bromine-chlorine bond would be nonpolar. Okay, because this is left to right on the periodic table. This is up and down on the periodic table. Okay, at a first approximation, this can tell you that. All right. Now, for our organic chemist friends, CH is considered nonpolar. Okay, just keep that in mind when you're looking at these. CH is considered nonpolar. From a chemical physicist standpoint, it is polar. But organic chemists, they rule the day, and so CH is considered nonpolar. Okay? All right. Now, these are polar bonds. But what about polar molecules? All right, now, what does it mean to be polar? So let's take the most simplest possible molecule, HF, and what that means is fluorine is a lot more electronegative than hydrogen, so the electrons are going to tend to be drawn towards the fluorine. And if the electrons are drawn more towards the fluorine, what we're going to say is the end with the electrons, because what's the charge on an electron? Electron is negative. And so the end that has more electron density is going to be partial negative. And the end that has less electronegative, less electron density is going to be partial positive. Okay, and so we have a plus pole and we have a minus pole, and that makes this polar molecule. Now, this is just two atoms, so not only is it a polar molecule, but it has a polar bond. All right, it is a polar molecule and it has a polar bond. So it has a plus pole and a minus pole. Now, let's take a look at another molecule. So let's take a look at this guy right here. Carbon tetrafluoride. And if we were to do the geometry on this, we would say what? 4 bonding, no lone pairs. This is tetrahedral with its geometry, okay? We would say it's tetrahedral. And we would look at this and we would say, you know what? That is a polar bond. Yes, it is. It's a polar bond. And we would look at this and we would say that it is pulling in this direction. We would. And we would say that this end down here, the carbon, we would say that's a partial plus. Everybody agree so far? Okay, yeah, no problem. Polar bonds. But what about the molecule itself? Now, I don't know how far you've gotten on math, but you may remember this term called a vector. A vector is something that has a magnitude and a direction. Well, that partial plus, partial minus has a magnitude, so many divides, and it has a direction. It's pointing towards the fluorine. All right. But if you were to take all of these vectors, what would they add up to? They'd add up to 0 because they're all pulling, so they add to 0. Therefore, nonpolar. Okay, another way of looking at this is that there has to be a net pull. You have to have a net pull in one direction or the other. And in this case, we're pulling equally in all directions. And since we're pulling equally in all directions, they cancel each other out. And so the overall molecule is nonpolar. The overall molecule is nonpolar. The bonds themselves between the carbons and the fluorines are very polar. They are very polar, the CF bonds, but the whole molecule is nonpolar. All right. So my point of this molecule, your first very simple molecule, is that you can have polar bonds and have a nonpolar molecule. Okay, don't get the two confused. Polar bonds are between pairs of atoms. Polar molecules, you have to add everything up. All right, now let's take a look at another molecule here. Let's take a look at this guy right here. I love fluorine because it's very electronegative. And if you were to draw it correctly, you would say this, and you would say electron domain geometry is what? Tetrahedral, electron domain, and the molecular is trigonal pyramidal. Okay, as far as the molecular geometry goes. 3 bonded, 1 lone pair. All right, what's the bond angles? 109.5, roughly. Okay. Actually, the bond angle between the fluorines will actually be less than 109 because, you know, the lone pair is going to push them together. All right, I'm throwing a lot of information at you, but this is the things you're looking at, right? Okay, so it's 109, but it's actually a little less than 109. All right, now is this molecule polar or nonpolar? Well, the first thing I look at and I see these guys are quite polar. The bonds themselves are quite polar. And it's drawing the electron density towards the fluorines in this case. Which direction are they adding up to? Well, they're certainly not balancing out. They're generally pulling down the middle of the axis this way. And so if you have a negative on one end, you've got a positive on the other end. So it's actually going down the middle between those fluorines. The fluorines being, let's make this a little bit more three-dimensional. These would be like poking out of the board. This would be in the board, and the other fluorine would be on the board. So it's going down right through the middle of them. All right. And so this is a polar molecule. This whole molecule is polar. The nitrogen fluorine bonds are also polar. The whole thing is polar. It's quite polar. The whole molecule is polar. Quite a bit so. Now, so that's generally how it works. Now, look. Now, if we're looking at a simple molecule or group, all right, there is a simpler way of doing these things instead of adding up vectors. Now, strictly speaking, you're adding up vectors. And so what you can do is do what I call same versus different. All right, same versus different. If it's the same all around, then it's non-polar. And if not, and if it's different anywhere, then it's polar. All right, let's take a look at a couple examples here. Let's take a look at CF4. We look here and we say same all the way around. It's non-polar. Let's take a look at our other example that we just did. And by the way, lone pairs are not the same as fluorines. And we would say different. And we would say this is polar. It's different. How about what do you think? Same or different? You look here and you go, it's different. This is very polar. How about water? Here's water if you do the Lewis dot, which by the way is a bent molecule. What do you think, polar or non-polar? And you look at this and you go, hey, I got this. Hydrogen, lone pair, hydrogen, different. Very polar. Same and different all the way around. Okay? Same and different. It's an easy way of deciding whether something's polar or not. All right, it's just to look around. And so I'm going to leave it with this. And let's see, let me make sure everybody can get in and out because I see people going in. Let's see, lock, unlock, there we go. All right, so, and within a molecule, particularly when you get into organic stuff, you can see this situation right here. Let's say we have this molecule right here with a bunch of hydrogens hanging off, and you got the carbon with the double bonded oxygen, carbon with the oxygen ion. Well, what do you think? Well, this end down here this end down here, remember what I said about carbon hydrogens not being polar as far as organic chemists go? This end of the molecule would be nonpolar, but this end of the molecule over here would be very polar. So within a molecule, you can have polar sections and nonpolar sections, and they become very important. And by the way, to finish up this whole idea here, how many resonance structures would you have here? 2? Yeah, you'd have 2 because this guy would go back and forth between the 2. See? That's 2 resonance structures. Okay, so this this acid group here, and this isn't what's called an O8, it would have 2 resonance structures. And when you get into organic chemistry, one of the reasons why this is favored right here, what I squared in with green, is because it's resonance stabilized. If you can delocalize that double bond, you actually make it more stable. And so this end of this molecule, not only is it very polar, but it's also been stabilized by resonance structures. Okay, all this stuff comes together. You see what I'm saying? It all comes together. All right. All right, that's it for that. So polar versus nonpolar, you should be able to look at a molecule and decide whether it's polar or not. So your ultimate skill here is to be able to do this. You should be able to start with something like this, like a phosphate ion. You should be able to go using Lewis dot structures. You should end up with something like this. Okay, this is the essential skills. I'm just diagramming out what you should be able to do out of this chapter. You should be able to go from there to there. You should be able to say 4 resonance structures. That's terrible looking. Resonance. 4 resonance structures. And you should also be able to say formal charges. Formal charges. And if we do formal charges, what do we have? We have, what is that? -1, 0, 0, -1, and -1. And you should also be able to say this thing is very polar. And you should also be able to say, what's the bond angles? Bond angles. And the bond angles on this guy are approximately what? 109. Because it is what? Tetrahedral. Do you see all the information out of that? From this one thing right here, we should be able to get the Lewis dot structure. We should be able to get the formal charges out of this. We should be able to get the geometry. You should be able to say whether it has resonance structures or not, and whether it's polar or not. All of these things are like a checklist. You know, you start with the formula and you go from there. Okay, so that's what this is really what chapter 9 and 10 is mostly about. It's mostly about, okay? All right, so there you go. All right, let's switch gears completely. We're going to switch gears completely to finish off this chapter. And this is the idea of hybrid orbitals. Okay, now, remember I say every now and then I say, you know, this model gives you this, and then we come up with something and we have to explain what's going on, right? Kind of like when we did this guy first. We said, you know, we could have this situation here. And you do know, I hope, that a single is longer than a double, right? And if you go and you look at this molecule and we said, you know what, it's not like that at all. It's actually a resonance, and we're saying that it's more like this, like it's you know, it's got partial, whatever. And what we're really saying is that this is a delocalized, that this is delocalized double bond. All right. And that's kind of what we said when we're saying resonance structures, we're saying things are delocalized. All right. So we're going to move on and we're going to say, you know what? Maybe they're not so much delocalized, but this is actually a mixture. Okay. So this is an alternative explanation as what's going on. Resonance structures, they can explain a few things, but really maybe what's going on is they really are a little bit of this and a little bit of that. Maybe they are for real. Okay. And so this is where we get the idea of hybrid orbitals. So if you remember, we had s orbitals, we had p orbitals. Remember that? Okay. And we can actually we can do bonding with these guys, and you can take two s's and you can bond them together. And an example would be like a hydrogen with the hydrogen, and they overlap and they make, you know, a hydrogen molecule. Or you can take something that has p orbitals. Maybe you can say, well, maybe the way carbons bond is maybe you can take two p orbitals, that's a carbon in the middle, and maybe you can overlap them. Okay, because maybe we're trying to explain how they bond in the first place. And so these are P's. Here's two P's, and there's the overlap. You see that? And so we're saying they're overlapping, and they're doing that. Now, the problem arises like this, particularly with carbon. Carbon, if you look, you would expect to have an s orbital. You'd have an s level and a p, s's and p's. Because if you look, carbon is what? It's 2s, 2, 2p2. That's carbon. If you look across, it goes 1s. I mean, the whole thing, if you count the filled inner shell. But if you just look at the valence electrons, it's 2s2, 2p2, and you'd expect to have s's and p's. What do s's look like? They're the round ones. And what do the p's look like? They're the, you know, the ones that look like double, like balloon animals. Okay. And if you were to do that, you would expect to have two very different looking, let's say if we had CH4, and I'm just from a very crude sort of way, you'd kind of expect the S's to overlap like that, and you'd expect the P's and the S's to overlap like this, like that. Okay, you'd expect them to overlap. And you'd expect two different kinds of bonds. You'd have the SS overlaps and you'd have the SP overlaps. That's what you'd expect. But when you look at methane, you have a tetrahedral structure where all the bonds are the same length. That's a problem. Okay, they're not different lengths. They're all the same length. So what's going on here? So what we're going to say is that we're going to say that they are mixtures between, we're going to say we're going to mix s orbitals with p orbitals. And if you talk to a computational kind of person who does works with big computers and try to calculate stuff, you would actually say, remember, an s orbital is a mathematical function and a p orbital is a mathematical function, and you can mix mathematical functions. If you mix one mathematical function with another mathematical function, you get a new mathematical function. Okay, this plus that gives you that. And so what we're really saying is we're mixing s character with p character. So if we mix an s plus a p, What we'll get is something that's kind of not quite the same thing. We have something that ends up looking like this, and this is called an SP. So this is an S and a P. And so we end up with something called an SP orbital. All right. Now, when we mix these things, we'd actually get two of them. So that would be times two. So we get times two. All right. So if you get one plus one, you get two. All right. And you can do the same thing. You can say an S plus two P's, and we get three of them. So that would be an SP2, and so we'd get three of them like that, and so forth. Okay, so you could have an S and three P's, and you get SP3, and you get four of them. All right. Now here's a pro tip. When you're trying to decide how many orbitals you're going to get, these hybrid orbitals, there's actually a 1 here. You see that? There's actually a 1 here. So what's 1 plus 2? 1 plus 1? It's 2. What's 1 plus 2? 3. What's 1 plus 3? 4. So you have 4 potential bonds that you're going to make. Okay, or 4 things that it can bond to. This is important. Okay? This is how we're going to decide what kind, because really, after all this explanation of like you're combining orbitals to make new hybrid orbitals, what does it really come down to? It comes down to, with our organic friends, this is all going back to our organic friends. If you have the following molecule, let me switch colors here. Let's go ahead and make, yeah, let's do this guy. I love doing this one. And we have to ask ourselves, we can, now remember we were doing this before when we were looking at bonds and bond angles, remember that? Remember all them bond angles? And it came down to, if you had two things, two bonded, we said that was 180 roughly, right? And if we had three things, we said that was what, 120 degrees roughly, right? Three things attached. And if we had four things attached, we said that was about 109.5, right? Because this comes from linear, trigonal planar, and tetrahedral. With me so far? Hey, it gets even better. Two bonded, SP. Because what's up here? 1 and 1. Remember what I said? Equals 2. And we look over here when you see SP2. Oh, wait a minute. What's over here? That green 1. What's there? 3 things. SP3. Whoops, let me change colors here. Make sure I'm consistent. And look here. SP3. And what's over here? That's implied. The green is implied. I'm just putting it there for clarity. Oh, look at that. Bonded to. All right, we're ignoring the number of bonds. We're just looking at how many things you're bonded to. Okay? Now, to get that bonding, you have to have the hybridization. Okay? So what does that mean? That means this carbon right here has 4 things bonded. That makes it what? SP3. This carbon right here has 3 things bonded. What does that make that? SP2. This carbon right here has 2 things bonded. What does that make that? SP. Life is great. It doesn't get no simpler than this. Okay. You do not want to focus. Do not try to not focus. Try to ignore these single bonded versus double bonded versus triple bonding. Okay. Just try to ignore them. It's hard to do. It's hard to do. You're going to look at it and you're going to see, like on that third carbon, you're going to see the 4 bonds. You're going to say, it's got to be sp3, right? You're saying it's got 4 bonds attached to it, but no, really, that's not how the organic people look at this. This is not how they look at it. Okay, they look at it as, well, there's 2 things bonded there, and so it's linear, and the only thing that's linear is if I hybridize an S and a P together, and then I'll get my 180 degrees that I'm looking for, and oh, yep, that's sp. Ignore. It's kind of like, Star Wars. The droids you're looking for are not here, right? Ignore the triple bonds. Ignore the double bonds. They're not there. All right. Well, they are there, but not for these purposes. And then you can go in there and you can also say things while you have it here. You could say, well, you know what? That's 109, right? What is that? That's a little less than 120. Remember that double bond, right? And you could look at this and say, you know what? That's 180. You see the bonds and all that? The bond angles? Yeah. You could also say, that this is long, medium, short, right? Relatively speaking, single bond, double bond, triple bond, right? What's the bond enthalpy? Single bond's less than a double bond, which is less than a triple, and so forth, okay? You can do all these things with this sort of thing. Okay, but this right here, this is the joke. You're trying to figure out whether it's SP2, SP3, or SP. That's the joke. You count up how many things are there. Keeping in mind the SP means 2, the SP2 means 3, and the SP3 means 4. That's what it means. All right, now the whole hybridization business, that's part of it as well. And so we can take a look at any arbitrary molecule and we can decide what do we have. Let's take a look at, say, let's take a look at benzene. Why not? Okay. It's going to bear with me. It's going to take me a moment to sketch this out. There we go. Got a hydrogen coming off, hydrogen coming off, hydrogen coming off. And just to make things even more interesting, let's make this a carbon with a hydrogen, hydrogen, hydrogen coming off. This actually is toluene. There's a T. Okay. Usually it's sketched out like this. And all that circle in the middle means it's a delocalized double bonds. Okay, but what's the hybridization over here? What's the hybridization on those carbons? Well, remember what we have to do? You have to count. Each one of those carbons in the ring, how many things are they attached to? Each one of these guys in the ring is attached to 3. That makes it what? sp2. All of them in the ring are sp2 because they're all attached to 3 things. What do we have here? And remember what I said, we don't ever put it up there, but there's a 1 there, right? 1 plus 2. They're all sp3. All of these guys are sp2. How about this guy right here, though? Well, that's attached to 4 things. So this is sp3. It's that easy. Okay, it's that easy for hybridization. All right, now, questions on that. How to identify what's sp1, what's sp2, what's sp3. Like I said, the big thing here, there's 2 essential skills here. One, you have to be able to count to 3 or 4, 3 or 4, right? You got to be able to count. The other thing is you got to be able to ignore how many bonds you have. You got to focus in on how many things are attached. to decide whether it's sp, sp2, or sp3. And by the way, there is higher ups. If you get into those hypervalent molecules like SF6 or whatever, they become like sp3d2. You start involving d orbitals, but we won't go down that path because our emphasis here is to get into the organic end. Okay, the organickers, they don't really care a lot about the hypervalent stuff. All right, now we have to look at, when we're bonding, there's also, now I kind of did this as an aside, but there's two ways. Let's take our p orbitals, and there's two ways of bonding. This part is the obvious way. You can do them end to end. End to end. All right? But there's another way of doing this as well. We can actually take two p orbitals and parallel to each other like this. I have laid them side by side, parallel instead of linearly. I've done them parallel to each other. Okay, so there's two different ways of overlapping with these p orbitals. Okay, and matter of fact, these have special names. So if they're end to end, we call this a sigma bond. And if they're parallel to each other, we call this a pi bond. Okay. Now, when we're talking, now remember, the emphasis here right now is towards our organic friends. All right, organic molecules. And so if we have a sigma bond, we will say all bonds have one sigma. If you have a bond, it has one sigma. All right. It does not have 0. It does not have 2. It has one sigma. Pi bonds are 1 pi for a double and 2 pi for a triple. Now look, if it's a triple bond, like here, you may be saying to yourself, well, why doesn't it have 3 pi's? Well, look, the first one is your sigma. Remember what I said? All bonds have one sigma. Okay. The next two are the pi's. How many bonds do you have total now? You have 1 sigma, 2 pi's, you have 3 total. You see how that works? So everybody has a sigma. And any extras are pi's. Now remember, last time I said, we have single bonds, double bonds, triple bonds, and then I said, do we have quadruple bonds? And I said, it's because they run out of space, right? Well, look, watch this. This is going to get busy in a hurry, but let me show you this. Watch this. So your first bond is that sigma bond, right? What's your second bond? Your second bond I'm not much of an artist, but I think I can pull this one off. Well, I tell you, these sketchy pads are fun. Look at that. You see how it's overlapping? Parallel. Pi, number 1. Now let's go out of the board into the board. This is on the board. Let's go 90 degrees out of the board. 90 degrees out, 90 degrees out, 90 degrees out of the board. We're going out of the board. I'm changing colors. I know it's getting busy in a hurry. But you see these guys right here. These are in the board, out of the board. Those are also parallel overlapping. So you have what basically amounts to being in the board, out of the board, in the board, out of the board. See, like that. And then you have the one running down the middle. So you got one running down the middle, and then you have, here's another representation. You see that? You know, I remember my professors doing this sort of thing in class. I remember when them doing this, and I was amazed. You know, and it's like, yeah, you know what? It after you do this for a while, it makes perfect sense. You can visualize these things, but you got to train your brain to look at these. Okay, so you've got one running down the middle, and you got the two that are at 90 degrees to each other. Okay, you got one running down the middle, you got the two that are 90 degrees to each other. Okay, now it's all 90s all the way around, and this is what's called orthogonal. This is not in your textbook, but it's called orthogonal, which means that if you take the vectors and you multiply the vectors to be orthogonal, the vector multiplication adds, you get a zero. Orthogonal means zero, that there's zero when you multiply them together. And so in this 3D space, the p orbitals between the pi and between the two pi's and the sigma, they're orthogonal to each other. Okay, and that's the only way it can work to get these to mix mathematically. Okay, all right. I know we're running over on the first hour, but I want to show you one more thing because I really, really, really want to do some stuff out of chapter 5. All right, I hope y'all don't object, but I'd like to work some problems out of chapter 5 when we get back. But I want to finish this up here. So let's take a look at our molecule here, or a molecule. And let's try to decide how many sigmas and pi's we have. How many sigmas, how many pi's do you have? Sounds like a fraternity. Sigma pi. All right. Now, what's the rule here? All bonds have one sigma. What's the other rule? Double, 1 pi, triple, 2 pi. Okay? So I like to just go through and the way I do this when I'm doing this is I'll look at a molecule and I'll just start marking them off. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 pi's. I just mark off all the bonds and I say, you know what? It's 1 pi for every bond, no matter what. I marked them off. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now I go back through and now I'm going to mark off the pi's and the double bonds and triple bonds. So here is a double, that's 1. Here's a triple, that's 2. 1 and 2 makes 3. So that has 1 pi, that has 2 pi's. 1 plus 2 is 3. Oh, and I left off 1. That's why it's important that you go through here. And then there's 1 more pi, and that would be 4. Do you see why I mark them? I go through and mark them. It's so that you don't miss anything. It's very easy to miss things on here. All right, very easy to miss things. And so that I miss any others, let's see, I got 2 double bonds and a triple bond. That'd be 2 plus 2 makes 4. So there you go. I got 4 pi's. All right. Like I said, just kind of, you should glance at the MO theory, molecular orbital theory. You should go through that and just kind of make sure you read it so that you know you've seen it. So, 2 years from now, someone asks you, have you ever heard of MO theory? And you go like, yeah, I've looked at it. And that should be good enough, okay, for MO theory. So we won't worry about MO theory. So what we're going to do is we're going to take a break. And when we come back, I'm going to go over